Good morning to those who are in America, good afternoon to those who are in Europe, and good evening to those who are in Asia Pacific. We have many different time zones at this time. My name is Marcos Sepúlveda. I am from the Pontificia Universidad Católica de Chile, and I will be chairing the third session of this workshop. In this session, we'll have three very interesting talks. The first one is a regular article, and the last two are forum articles. These articles are presented as ongoing research, so as the authors will welcome any feedback you can provide them about their work. The first talk will be presented by Juan José Lul Noguera from the Universidad Politécnica de Valencia and is entitled Exploration on How Global Warming Affects Emergency Services. So, Juan José, you can share your screen. You can start.
Now I've unmuted and I didn't start the video. Okay, both those two things were important, and now I'm going to share my screen to. Okay, so let's start. So as thank you very much, Marcos, for presenting me, and I'm going to talk about the exploration with process mining and exploration on how temperature changes affects hospital emergency departments. This is going to and the outline of the presentation will be first we'll go through the introduction, the materials and methods, results, discussion, and the final acknowledgement. So it's basically what we have presented in our paper that you can see in the website, in the PODS4Health website. If you've seen the WOBA application, it's not what's uploaded because it's another previous version, but you can see it there. So we're going to see how we're going to see that ED, that's emergency departments. We're going to focus on the processes in emergency departments, that they are complex, they're not adaptable from one ED to another. And we will see also by the other side that the global warming we wanted to tackle. And there's a temperature increase year over year. And there's also harsher weather conditions, specifically heat waves and also sudden decreases in temperature. Both are things that are related to have been shown and proven that they are proven, maybe it's a too strong a word, but they have been shown that they are related to global warming. So they are climate change effects and in the end effects from global warming. We're going to see how we approach this study, and it was through interactive process mining. Interactive process mining, it's a mix that brings by one side a data-driven approach. As in machine learning techniques, we start from data and start extracting information. But at the same time, it offers a human understandable view as in knowledge-driven techniques. So we will also be able to very easily understand this model, and also it will be very easy to understand by clinicians who will be able to even modify the workflows that we will see from the processes. So it's we believe that's mixing the best part of both worlds of these data-driven approaches and also human understandable knowledge. And we will also focus on interactive process indicators as compared to key process indicators. The IPIs, interactive process indicators, use process mining technologies to provide rich graph-based indicators that bring a human understandable view that supports the expert in the better perception of the processes for advanced assessment. So let's start with this IPI that we start with, and that has been validated by the clinicians. So we have we have a start node and an end node that we'll always have with PM app that we have used, and all the traces start in the log with start and end. And this represents already the 400,000, approximately 400,000 records that we have in a hospital in Valencia, and this also represents it was around 200,000 visits, because the same patient can go once and again. And so I said that this was the process. Let me just check, take the laser pointer. So all the patients go to arrival. So when they arrive to the hospital, they present their card and their identification, and then there's a timestamp that's assigned to them. So we have an initial event. Then we have the triage, where each patient is assigned to one of 5 queues. So the first queue, waiting queue, would be highest emergency. So they have to attend this patient very fast, in a very, and it goes down to wait 5, to patients that will have to wait a lot, because what they have is not so urgent as in queue number 1. Then they are all attended, and we have created this artificial differentiation. So we have one only attention, but then we separate them because we want to measure how the Q1 affects to those people who have waited in Q1 and are attended. And the same goes for each and every queue. In the end, in this process, people go, after being attended to, they go back home, or they are admitted in the hospital, or there's a final death of the patient, or they can go to other ends, maybe a transfer to another hospital, etc. And in the end, we have, as we said already, this end node. One thing that's very important here is that we can have the execution number we have the number of visits that have gone through this process. We have it coded in colors. So we have from red color, to see from this node start to arrival, we have a red arrow, a transition. And so what we see here is that what we have coded here is from green to red. The greener the arrow, the less number of executions, the less number of traces also, and the redder the color, the higher number of executions. So in this case, for example, we see that there have been many more visits that have gone to wait 3 and wait 4, as expected, than to wait 1, wait 2. In this case, wait 5 is a queue that's not very much used, let's say. That's about the execution number. So we can see where people are going. For example, we see visually here that from attention 3 and attention 4, most people go home also, and the same happens to the rest of the queues. We have also coded here the median duration. So we have a lot of information in this graph, and that's the nodes, they have this color. And as you can see, in wait 3, we have a redder color, wait 5 redder color, and the highest red colors, it's basically in attention 2 and attention 3, then attention 1. And this means the duration that we have taken the median from the patients and taken this duration. So in attention 3 is the highest time that's spent in a node, in an activity, in this case in attention. And then we can also see that people wait very, very little in wait 1 and wait 2, and they wait a lot more in wait 3. And interestingly, they wait a bit more in wait 5 than in wait 4, in queue number 4. So let's go on with the material methods. We can see that, as I said, there were 400,000 visits, and it was around 150,000 patients that went to the hospital, to this same hospital, from 2015 till 2018. And we focus on how temperature affected these EDs. this emergency department, basically by one side measuring with high temperatures. We made a division, artificial division of temperature groups, so we could see how it affected, and also how harsh changes affected. For this, what we did was measuring day-to-day temperature increases and also day-to-day temperature decreases, and try to see days that from one day to the next day, they had a very high increase in temperature or a very high decrease in temperature. So for the results, we have two IPIs, two processes that we can see process indicators. And in this case, we're seeing heat strokes. And as you can see, there are many more heat strokes, of course, for the 25 to 30 degrees Celsius. And that most of them go to the Q number 3. And we can also see that the attention in weight 2 is way higher than the rest of them, because in these two process indicators, the duration and also the execution numbers, the color is shared between them. So this means that, for example, it is going to weight 3, this transition takes more people. There are more people than here and here. And okay, that was one of the results. We didn't find there were not enough results from 30 to 35 degrees, because we don't have Valencia is a mild weather city. And we also see that we have, this is attention 2, and then you can see that the highest time was in attention 3 in 20 to 25 degrees, and then attention 4 in 25 to 30 degrees. And it was very more interesting for us, and it was most interesting seeing how the results in harsh increases and harsh decreases. So as I said earlier, and you can see in the methods in the paper, we separated with those days that had harsh increases and steep decreases also from normal days, let's say. And we separated those groups, and this to the IPI for normal days, this for the increased temperature days, and this for the decreased day-to-day temperatures. And we can see here that by one side there was so includes number 2. Well, sorry. In attention 2 and attention 3, this yellow circle around, it means that there was statistically significant differences. But we can see that there's a difference in the time it takes longer to attend people in attention 2 and attention 3 queues compared to the mild temperature days. And also there's a higher time that's spent in triage, and the same happens to the decreased temperatures. And we also see that there's also a higher waiting time in weight 3 and attention 3 in those days that have a decrease in temperature. So for this discussion, we would like to say that I would like to say that there's heat waves, and it is has caused the maximum number of deaths in recent years. So it's interesting to study that. Also to see that in places with that don't have these mild weather conditions, or they can have the emergency departments would be overwhelmed, especially if it also happens with within holiday seasons, that maybe there are also less doctors. So this is my second point. And I also wanted to stress that the global warming effect that we focused on, it was those days with harsh weather conditions, so those small temporal windows with harsh weather conditions, because we're increasing 0.18 degrees Celsius each year. So we are more interested in those extreme weather conditions that would make, they are making already these differences in the attendance, in the attention and waiting time in the emergency departments. So thank you very much. I would also like to thank EIT Health that has funded our research, and thank you also questions that you will have. I'm here waiting for you.
Yes, thank you very much, Juan Jose. I didn't interrupt your presentation, but we had some problems hearing what you said. Uh, uh, um, I hope that that didn't jeopardize the attention of the audience. So we have time for some questions. I switched off the video of many of you. So if you want, you can start them again. Now we can see you, Juan Jose. So I have some questions for you. You showed the difference you found, and I wonder whether those differences are statistically significant. Have you checked that?
Okay, so Marcos, I'm sorry because I had problems listening, so I didn't hear anything. Could you please repeat the question? I'm very sorry.
Okay, so you found some differences between different days, and my question is whether you check if those differences are statistically significant.
Okay, so yes, we found that they were statistically significant for some of the days, and that's what I showed you. I can hear also echo, but okay. So I showed you through this slide. Okay, so this one was statistically differences between attention to in mild and increased sensor days.
Sorry, Juan Jose, we cannot really listen to what you are saying. I don't know if Carlos can complement your answers. Please try again.
I can tell something about the statistical significance. The application that we are using is called PMAP, and the idea you could create this kind of IPIs we call. The IPI is as I said, Juanjo, is a process-based KPI in order to present in a graphical way what is occurring, and as is a indicator, you can compare indicators. So we have operations between the different flows in order to make comparisons. One of the tools that we have in that is the application of statistical significance. We apply a classical student in order to apply what is the difference between the nodes, and we put what are the differences in yellow rings. So the nodes that have yellow rings are the one that have a statistical significance below 0.05 in the p-value, for example, in that case. So for that, we detect what is the specific emergencies in rooms depending on the data.
Okay. Thank you very much, Carlos, and thank you very much, Juan Jose, for your nice presentation. We will continue with the next presentation in this session, which is very tight. So the second talk of this session will be presented by Nick Fatina Farid from the University of Leeds, and it's entitled Modeling the progression of frailty in elderly people using process mining and the EFI frailty score. So you can share your, Nick, you can share your screen whenever you want.
Hi, thank you, Marcos. Let me share my screen. Can you see it?
Yes, we can see it.
All right. Very good evening to all of you. Thank you, Marcos. So, hi everyone. I'm Nick Farid from School of Computing, University of Leeds, UK. So here I'm going to present to you one of my work in my PhD, entitled Modeling the Progression of Frailty in Elderly People Using Process Mining and the Electronic Frailty Index Score. So this is the work between us four, me, David Multicams, and Owen Johnson. So here is a little bit outlined about what I'm going to present today. So I'm going to look into the background and some definitions that I'm going to use throughout throughout our work. It's the definitions are frailty, electronic frailty index, and polypharmacy. And for this work also, I'm going to use a ground methodology, which is a process mining project methodology that consists of 5 stages. There are planning, extraction, data processing, analysis, and evaluations. So in this case, it is not essential to include the process improvement and support yet. And then next, going to go into the discussion and the conclusion that include limitations and the future of this work. So for the introduction, so frailty, what is frailty? We go into the definition of frailty first. So frailty is a common condition experienced by elderly people, and the progression of frailty is seldom reversible. So it is common in the elderly. So it's affecting about 4% of people aged between 65 and 69 years old, and 26% aged 85 years and above within the UK population itself. So frailty is a geriatric condition that any distressing event may dramatically accelerate the failure functional of physical, mental, and health in frail person. So it include the distressing event may include such as infection to virus or change in medication and etc. So all this will result in increased risk of hospital admissions, institutionalizations, and adverse health outcomes. Thus, early identifications of frailty is essential, especially during routine assessment. It is to support proactive targeting of the most vulnerable for healthcare interventions. So with a view to reduce risk of adverse outcome. So there are a variety of tools to identify frailty that has been developed that include PRISMA-7 questionnaire, Tilburg Frailty Indicator, FI share, and etc. However, all the frailty tools mentions required high amount of guidance, time, specific equipment, and resources, which may introduce some delay and slowness during elderly patients' clinic checkup. And therefore, the electronic frailty index has been developed and validated to calculate a frailty score using routinely collected health records, and it is now routinely adopted within the UK primary care setting. So another reason why it is adopted within the UK, it is because it is very efficient in stratifies older patient via calculated score. Next, so in this work, we are going to explore the potential to use process mining as an approach to model frailty pathway using the EFI, or the Electronic Frailty Index Score. Frailty progressions can be viewed as a dynamic transitions of several states in sequence order from healthy aging to pre-frail and frail. But in our case, we are going to define the transition states of frailty, also known as the severity of frailty. So the transition states will be named as clinically fit, and then go to the mild, moderate, and severe. So this also will be known as the common sequence of frailty progressions. So frailty progressions. So in this work, we're going to look into the common comorbidities found within the elderly, which are hypertension, fall, and polypharmacy. So here, the next definition that we're going to use in our work is polypharmacy. So it is conditions of simultaneously use of multiple different types of medication by an individual. So for the hypothesis of this research of work, so frailty progressions can be modeled with the electronic frailty index score, which are readily available within the electronic health record. So here, we're going to the next session, which are planning and extractions. So for this work, we have created two research questions we have identified two research questions for our work, which are, the first one is, can process mining identify the significant progressions of frailty within frailty category? And the next one is, can process mining reveal whether polypharmacy contributes to worsening frailty for patients within different frailty status? So here for the extraction, we're going to use electronic health record extracted from the primary care setting in the UK hospital or UK GP practices. So the record should be within a year of 2003 until 2018. And the patient age that we are selected is at least 64 years old and above. So there are two selection criteria that we have listed in this work. And excuse me. And then we got about 10,317 patients. And in this record, they are using a read code version 3 with a total amount of 2,069 thousands of read code. So the next one, for the data processing, we include three steps of data processing in this work. The first one is log enriching. So in these steps, we are getting additional events for our log, which are polypharmacy and to calculate the EFI score. So for your information, polypharmacy is not included together in the patient record. It's in separated record. So we have to get the list of medication prescriptions. And then we work with the pharmacists to identify the medication that is prevalent within the elderly patients. And then we got 4,762 different types of medication within the elderly patient using the first 6 characters of British National Formulary Code. And then the next one is we're going to calculate the electronic frailty index score for our data in our record. So EFI score is a calculations of ratios of deficits that present to deficit evaluated for a given individual. So here deficit is referring to a disease in the patient which has been identified by our expert domain. So the total number of deficit for our case is 36, including polypharmacy. And then we have, after we have calculated the EFI score for all the patients in our data, so we have 4 category of frailty, which are clinically fit, mild, moderate, and severe. And for information as well, we got the final, we got the frailty category based on their final record in their electronic health record. So that's how we obtain their frailty category for each individual patient. So here, in this table, the accumulated deficit range for clinically fit is between 1 to 4, and mild is 5 to 8, moderate is 9 to 12, and the severe is 13 to 36, and their score range that's shown here. Next steps in data processing is aggregating events. So this step is designed to reduce the number of duplicated events and to reduce the complexity of the model. So we did it by aggregate the similar deficit with a similar recorded timestamps. And the next steps in data processing is the log filtering and converging. So here, for our case study, we are going to look into the frail patient only. So we're going to remove the clinical fit patients and include only patient from mild, moderate, and severe category. So we partitioned the log into 3 separate logs accordingly to their frailty category. So here in this table is the summary of each event log. So we have 3 frailty category: mild, moderate, and severe. And we got high number of cases in the mild category, but high number of variants in the severe category, because we got high number of activity in the severe category. And then, sorry. So here, the number of activities for each frailty category is different, 5, 6, and 7. For mild, we have 5, moderate 6, and severe is 7. So we're going to explain that next. And then here and next, we create a frailty step graph to show whether there is different growth of progressions that happen within different frailty category over time. So how we did it, we randomly select 2 patients from each frailty category and gave the same start point as first event baseline, which is the first day in the year 2000. Here, and with the rest of the event according to the real duration between them. So here, the severe group can be seen to have a sharper increase in score, representing a rapid decline into frailty. So the cases in the mild is the yellow one. So the cases in the mild group show a shorter case duration as compared with the other cases. So what we get with this illustration is that so this will act as our starting point of cases in this step graph that allows us to directly compare the comparability of the progression. So, however, we still need the full data sets is required to understand whether the examples is really typical or is really significant for the population. And the next, for the analysis, for the mining analysis, for the next analysis, we use one of the plugin in the prompt, which is Inductive Visual Miner, to answer our research question 1, which is can process mining identify the significant progression of frailty within frailty category? So we got 3 process model here for mild, moderate, and severe. We look 3 different, we look 3 event log into the prompt. And then generally, the similarity that we found between these process models is that we have the presence of hypertension and polypharmacy. They always present at the early stage of the process, means that it can happen before clinically fit or in between fit to mild stage. So, and the primary distinctness, primary difference behavior that we can observe is that fall deficits only occurring in the moderate and the severe model after a polypharmacy event occur. A fall may occur at any time, but its infection can be more severe in already frail patients. And the next behavior that we can see is that polypharmacy is common towards the end of the mild frailty, and more frail patient with polypharmacy appears to happen before other important events such as fall. And then next here, we do cross-conformance checking on event log to assess the model comparability. So here we found that my model has the lowest fitness value, indicating the inability to produce the trace present in the event log, which also suggests that it's a different model of each category and we should treat it differently. So in order to answer our research question 2, which is, can process mining reveal whether polypharmacy contributes to worsening frailty for patients within different frailty status? So here we're going to adapt the process log analysis. So where we treat each frailty stages as a different individual block. So here we're going to investigate the transition stage that happened within different frailty category. So here is a frailty frailty stage transitions that it occurs from clinically fit to mild, moderate, and severe. So the first block S1 is the transitions that happen between fit to mild, S2 from mild to moderate, and S3 from moderate to severe. And then we're going to look into the polypharmacy deficit here, at which particular block that it's commonly occurring in our case, in our work.
So Nick,
yeah,
we're running out of time.
all right.
Go to your final conclusions.
So yeah. Okay, I'm going to go a bit fast now. So, all right. And then we implemented statistical approach on measuring the p-value to find a significant difference. So here we implemented ANOVA to find a significant difference between group of 3 or more and the t-test for 2 groups. So here we found that the interblock of interval mile category had significantly longer interval than the moderate and severe categories, but no significant difference was found between the moderate and severe categories. So here also it suggests that in block S1, so both moderate and severe categories deteriorate statistically significantly faster than the mild category after polypharmacy. And then we further analyzed the S1 block only, so as it has the majority of the traces and all category has been through the frailty transition from the clinically stage to mild. So here we use the interactive data of a heuristic miner in prompts to generate a model based on the frequency of the activities in the model. So the similarity structure that we found here is that P2 mark that found in the mild and moderate model. So here it shows that this mark is not shown in the severe category. So the distinct structure that observed in the severe category shows the patient can either start with either being clinically fit or hypertension or polypharmacy, any of that. And there's also another path executed from polypharmacy to clinically fit, which is none in the other 2 process model. So here indicates that polypharmacy is common as the initial activity in the flow for the severe category. So here, the representation of the process model is similar.
Nick, I'm sorry, but I have to finish your presentation. Can you just quickly go to your
conclusions? All right. So here in this work, we have included the application of process mining technique within the elderly domain in the primary care setting. So here also we have demonstrated the different progressions of frailty category. However, we have one limitation here. So once an individual was characterized with polypharmacy, they were assumed to be exposed to polypharmacy for the duration of the whole study period. For our future work, we're going to understand more on the interactions of combination of frailty deficit with frailty progressions. And we're also going to look into the presence of polypharmacy at multiple points along the study duration and using different definitions of polypharmacy, also known as hypopolypharmacy. That's all.
Thank you very much, Nick.
Yeah.
I'm sorry, but we ran out of time. We don't have time for questions. So I will encourage everybody to provide feedback to you by using the private chat in the Zoom session. And I thank you for your very interesting presentation.
You're welcome.
Next, we will go to the final talk of this session that will be presented by Kifan Chen from the University of Sydney, and it's entitled "An Algorithms to Preserve Infrequent Relations in Process Mining and Application to Lab Test Ordering Processes." Kifan, I think you're ready.
Yeah, thank you. May I just share my screen now? Give me a second. So thank you for having me here. I'm Kevin. I'm first year PhD student from the University of Sydney. Really happy to be here to present my paper titled as "An Algorithm to Preserve Infrequent Relations in Process Mining, an Application to Lab Test Ordering Process." So process mining is basically is a newly applied technology which connects the computational intelligence, data mining, process modeling, and analysis approach. So it actually bridges the gap between process science and data science. So nowadays, because of the healthcare and medical field have drawn significant attention this year because of the rapid growth of the electronic health records. So this actually provides great opportunities to analyze certain processes from different perspectives. There are a lot of applications on healthcare recent year. You can use process mining to analyze the central treatment pathway for a certain disease. You can also use it to analyze the internal relations. For example, internal relations between the aggressive behavior in residential care facilities. You could also use this to analyze the performance, such as the waiting time for patients. However, most of them only pay attention to the primary pathway and ignore the infrequent relations. So infrequent relations are defined as the directly follow relations between activities that rarely occur in the event log. Certain relations are dependent on the outcome of another activity. So that is to say, the outcome of the previous activity will determine whether the later activity happens or not. In many algorithms, there is a predefined threshold. If the number of the occurrence does not reach the threshold, the relations would likely to be discarded. However, this kind of infrequent relations may retrieve important insights. Let's just take in the below diagram as an example. This is actually a process from the emergency room transfer. So the primary pathway is actually ED registration, admission, doing some lab tests, then transfer into different care units, and finally discharge. Nevertheless, there are also few infrequent traces. After performing some lab tests, the patient are directly discharged. In normal process mining algorithm, the lab test to discharge relation will be removed, which I already using the red square to show that relationship because this is infrequent. However, this is due to the lab test result of the patient is normal and the patient no longer serves as an emergency and then discharged from the emergency room. That is to say, the condition lab test results normal triggers the infrequent relations from lab test to discharge. This infrequent relation should not be removed, and it provides us with the useful information about the process. So which brings my goal for this paper. So our goal is firstly, we want to identify the infrequent relations between the lab test in different diseases. Second, we also like to identify the value-based conditions that can trigger these infrequent relations. And last but not least, we would like to preserve the useful and precise value-based conditions which trigger these infrequent relations. So for the methodology used, for the data we use, we're actually using the data from Mimic3, a public available data set. And we also applied and modified the LSTAR lifecycle to serve as a pipeline for our application. And we also proposed a novel data pre-processing approach, which can automatically detect and aggregate the events within the same case that has the exactly same timestamp into a single event, which will reduce the unwanted directly follow relations because we can't really decide the internal relations between the events which has exactly the same timestamp. We also apply the data-driven heuristic miner to mine the infrequent relations and the value-based conditions. And last, we use the confusion matrix to assess the accuracy for the conditions we find and the discard or preserve the useful ones. So the entire pipeline is shown in the below diagram, which I will explain later, detail in later. So the first step is actually we came to extract the data from the MIMIC3 dataset. So MIMIC3 stands for Medical Information Mart for intensive care. It is actually a public available dataset which is divided by the MIT teams. It records the EHR information relating to patients admitted to the critical care unit. So there are several tables in the MIMIC3 dataset we used in data extraction. The D-lab items describe all the lab tests in the dataset, which serves as a dictionary. Lab test contains all the lab measurements for patients, and we adopt check time as timestamp in the event log. DICD diagnosis is also dictionary, which has all the disease along with their ICD-9 codes. Diagnosis ICD has all the diagnosis of patients and coded using ICD system. Patients contain the information of patients, such as gender. So among all the different lab tests, we actually spot 12 common lab tests from the MIMIC3 dataset, which is shown as the on the left-hand side table. We cover some common lab tests such as ALT, ferritin, sodium, and potassium. So since our application task is to identify the lab test ordering within each disease, so we also adapt 5 different diseases in our application, which is shown on the right-hand side table along with their ICD-9 code. So next, I would like to give a summary of the dataset. So for each disease, we actually split the dataset into female and male. We would like to using one dataset to mine the relations and using another dataset to evaluate our conditions. So as we can see, so there are total 10 different datasets in total. As we can see, actually the dataset is quite large. Most of them are over 5,000 traces. They have 100,000 total events. And some of them even have like over 500 events in a single trace. So next is actually we apply the value-based condition. We identify the value-based conditional infrequent relations. This is actually achieved by applying the DHM plugin, which is the algorithm I proposed before. I talked before in the program, and we're using lab test result as attributes. So how the algorithm works is actually it first determines the frequency of every relations. And next is identify the infrequent relations, which is a predefined threshold. And next is discover the conditions based on attribute values using some machine learning skills, such as decision tree. And next is evaluate the conditions, which also use a predefined threshold. The last 2 steps is actually we need to make sure the output of the CNET is connected. So we're not going to pay too much attention here because our primary focus is not instead of the overall diagram. We're more focusing on the infrequent relations and their conditions discovered by this plugin. So for the evaluation, we also make 3 different criteria to discard some of the relations. First, we exclude the relations which contains the artificial start or artificial end, because the DHM plugin adds these 2 activities to corresponding to the requirements of CNET. It actually makes no real sense. For example, we have relations like sodium to artificial end will be discarded, which represent a discard 1 in the table. Since we're also interested in the conditions divided from the previous test results, which may trigger another test. So all relations with no such conditions will not be included, writing as discard 2. For example, the sodium to glucose relation with the condition potassium results larger than 12 will be ignored because the condition is irrelevant to the sodium result. The condition we actually want is actually sodium result small or larger than something. So the condition here find is irrelevant with the relations. So also we calculate the accuracy based on the confusion matrix. We will discard the certain condition if they achieve very low accuracy, because this means it's not consistent in both data sets. We calculate the true positive, true negative, false positive, false negative, and last we calculate the accuracy. The accuracy threshold we use in this application is 0.7, which means the conditions which achieve 0.7 below threshold, below accuracy will be discarded. So here comes the result. In total, we successfully identified 24 infrequent relations out of 5 diseases. Among them, 12 relations are discarded because of the evaluation standards, and the rest are preserved. Most of the infrequent relations we found occur less than 10 times in the event log. We regard the rest 12 as the useful relations with value-based conditions. Among the 12 removed relations, 5 are due to accuracy below 0.7, and the 4 are because of containing artificial n. Each relation is evaluated using a separate data set and the method proposed before. On average, the preserved relations achieve 87% accuracy. The highest accuracy is 97%, and the lowest one is 70%. So let's just give an example. So taking the disease ICD-9 42371 as example, we pick the female data set and find 6 infrequent relations. One infrequent relations can be after the patient going through a set of tests, which including ferritin, potassium, and sodium. They may be asked to go for sodium test under some circumstances. The conditions for each infrequent relations are also presented. For example, the conditions trigger the highlighted relation is sodium result smaller or equal than 128. So we can interpret the condition in this way. Normally, the relation will not frequently happen in reality and are considered as noise. However, suppose the sodium result for a patient is smaller than 128 during the set of tests, which including ferritin, potassium, and sodium. Then the patient is very likely to be asked to be performed another sodium test afterwards. So to conclude the paper, we actually apply the mimic3 data to find the value-based infrequent relations between lab tests among different diseases and try to retrieve the important insights. We successfully identify several infrequent relations along with their value-based conditions, showing it is consistent among different datasets. The future research could be using domain knowledge to evaluate the relations and the conditions we found. And that's the end of my presentation. Thank you. Any question will be welcome.
Thank you, Kifan. Very interesting your talk and your work. We have time for just one quick question, and I will again encourage everybody to give you feedback using the private chat in Zoom. Does anybody want to ask a question? So, okay, Renata Medeiros, please.
Yeah. Can you maybe elaborate a bit more on how do you see the difference between infrequent behavior and noise?
Yeah, so basically, saying like the infrequent relations will be kind of nowadays the discovery algorithm will likely to use the frequency to determine whether this is noise or whether this is not. But so saying whether this is actually noise or is actually infrequent, but which provides some useful insight, we can't really decide it. So we try to make use of this one to say, okay, so for the infrequent one, we can't just simply, okay, I want to get rid of this, all of the infrequent one. We want to take a look at the insight. If the insight makes sense to some, like say, it's consistent in both data set, so that means it is not noise. It's actually a consistent phenomenon. It's just infrequently happen. And for future, we can also say we find some conditions and find some infrequent relations. We could also use it, ask some domain knowledge, a domain expert to evaluate this. If they say oh yeah, this is what happened in the hospital, so that this may not be regarded as noise. This is just a phenomenon but it's just infrequent happen. So that's from my opinion, what's the difference between noise and infrequent one.
Okay, and the idea to evaluate if this is indeed infrequent and not noise would be through domain experts?
I think the question is, did you get the question? Did you get the question?
I don't quite get the question.
I think what Renata was asking was whether you work out whether it's significant by asking domain experts.
Yeah, that's actually we actually don't implement this step for now, but we're happy to take this as a future research direction.
And just
evaluate our result. Yeah.
And my understanding was that what you're doing that's novel is that you're looking at the attribute values on the pathology results to understand that in this particular case, this infrequent event was actually clinically significant.
Yes, exactly.
Yeah.
Okay, thank you very much, Kifan.
Thank
A
you.
very interesting
well
talk,
done.
and I would like to thank all the speakers in this session for their very interesting talks. And I will give the floor to my colleague Carlos Fernandez Yada, who will lead the final panel of this workshop. Thank you very much. Carlos?
Carlos, you're on mute.
Carlos, you are mute.
It's always better that way.
See, when you get the presentation, you lost the menu to get.
It jumps somewhere else, yeah.
So don't worry. Yeah. Finally, we are a very short time to talk about the panel. What is the final presentation of this day, on final presentation of the PODS. In this panel, we talk as every year about our alliance. What are the new ideas that we are working on 2020, this strange year, because we have a lot of problems this year. So even of all the problems, we can see that the number of publications are growing more and more. You can see it in Google Scholar. You can see easily in the number of publications that we have more and more publication of process mining in healthcare. But the important thing also is the publication that we have in PubMed, because it's not only the publications that we have in general process mining applied to healthcare, but the important thing is PubMed is the one of the best texts about publication in medicine, and we are growing a lot the presentation of process mining in the medical domain. So I think this is the way to go to present that to doctors, and our tools should be using in real environments. So it's a very nice index to start working on that. But so the moment is now. The moment is now in order to create this research in order to support the medical community. So in PODS, we have some initiatives that we are working year by year. And for example, according to initiatives, we have made a brainstorming, that is leads by Niels. Niels, you can talk something about the brainstorming?
Yeah, sure. So we had back in June 2019, in the good old times where we could meet in a physical location, we had a brainstorm seminar where we focused on 2 days thinking about the question, how can we enhance usability and understandability of process mining in healthcare? So we had very good discussions with an international panel of 18 experts, both from process mining community as also from healthcare partners. And based on that, we wrote a paper with some recommendations on how to enhance usability and understandability of process mining in healthcare. And that paper last week, right in time for this workshop, got accepted and published in Artificial Intelligence in Medicine. So the paper is available. If you want to read it, I will share in the chat also a link where you can still download it for free. That is not behind the paywall. So definitely worthwhile if you want to see what we came up with in terms of recommendations based on the seminar.
Thank you. And also we have a new special issue in Journal of Medical Informatics. That is very nice journal and have a very good position in the medical domain. So Jorge, you are leading that initiative, and you talk about that.
Sure. As Carlos said, we had managed, actually it's also last week that it was the final call was published. So basically this is a premiere. We have an open special issue for the Journal of Biomedical Informatics journal. This is one of the most important biomedical informatics journals that there is. It's the Springer. So the call is gonna be due to 1st of June. It's gonna get open in February, so you have plenty of time to work on your approaches. As I said, it's going to be an open special issue. This means that you don't need to have a paper accepted in PODS to submit to this journal. And also all the papers that got submitted before 1st of June, they are going to be published also open something.
Open access.
Open access. Thank you very much, Owen. It's going to get accepted open access. Thank you very much.
So a third idea is a book. We have created a book about interactive process mining in healthcare. This book will be available in a few weeks. We have the last proof this week. So in 2 weeks or 3, we have this book open now to go to see you in Springer. Also, we are also promote and lead several projects in different calls. Also, in that case, we are working in different European, different national, different regional and local projects. And for example, we have 3 projects in European projects that we call Life Champs and in advance for palliative care analysis analyzing the palliative care flows in order to allow what is the best flows to take care of people that go to die. And Value Project is it has 80 health project that the main idea is to create process mining tools for supporting different ideas in hospitals. In fact, in this project, there are 6 hospitals. 3 of them are from the Big 9. That is the big 9 hospitals in Europe. So it's a very, very huge project also. But we want more because the idea is to improve the presence of this kind of project, this kind of research in the medical community. Also from the community, we're looking at the idea of call for members. The idea is to make support to the Alliance in order to create new ideas, new projects, new research brainstormings, or new ideas to start working on that. We are 6 people in the steering committee, but we are trying to get more people working more and more on that in creating this kind of thing. So we have had a subscription in this web page, in the PODS web page. We can subscribe in this alliance link. And for start making the discussion, we have created, Jorge has created a channel in the WOBA about process mining in healthcare, and the idea is to ask for research collaborator, process partners, and all these kind of things that is very interesting to start growing in the not only in process mining but also in healthcare domain. And the last one on the list, we go to the awards. The final idea that most of you are waiting for that. The idea is to what is the best student paper award and best paper award, and the best student paper award first. So, and the winner is the process mining on fire and open standards based on process analytics and process approach for healthcare. For Emmanuel, Oliver, Anna, Andreas, and Joseph. Okay.
Thank you very much.
Congratulations to the winners. And finally, the best paper award of this year was to delivering a sophisticated clinical pathway based on patient conditions from electronic health record from Junjon, Idong, Minshu. Complicated to me to see these names, but congratulations to the authors. So finally, see you next year in Eindhoven. I think I hope we finally see presentially in Eindhoven. If not, we can see in this virtually way. Probably cheaper to go all together, but I think it's better to be in touch, better in presentially way, in order to make a better sharing of our thoughts. So thank you very much, and see you next PODS.
Thank you.
See you.
Thank you, guys.
Bye-bye.
Bye, everyone.